Welcome to Zero Knowledge, a podcast where we explore the latest in blockchain technology and the decentralized web. The show is hosted by me, Anna.
And me, Frederick. In this episode, we sit down with Benedict Bunz to deep dive into bulletproofs and verifiable delay functions. Hello and welcome to Benedict Bunz to this episode on bulletproofs. I'm super excited about this topic. I know you work on not only bulletproofs, but a lot of other interesting things. I mean, we'll get some of that too. But maybe you can just start with a little bit of an intro of yourself and talk a little bit about what bulletproofs are.
Yeah, cool. Thanks for having me here. My name is Benedict Bunz. I just finished basically the second year of my PhD at Stanford, where I work with Dan Bonnet on, sort of generally applied cryptography with a special focus on cryptocurrency. It's really sort of, the technical details of cryptocurrencies and the cryptography, the things that, make it secure. So my focus is on that in recent times, I've been, for example, working on bulletproofs that I guess we're going to cover today. And then also, other stuff like verifiable delay functions, light clients and sort of a whole variety of topics.
Cool. And this is actually the second time you're on this podcast. We had a very short interview with you on the ZKon0 episode. I'm really excited to get a chance to continue our sort of series on actual zero-knowledge proofs and zero-knowledge technologies. Bulletproofs very much fits into that category. Do you want to maybe just start off by helping us understand what bulletproofs are?
Yeah, so bulletproofs is a zero-knowledge proof. So, their zero-knowledge proof is sort of the general technology, and then there's sort of many different flavors of it. Like one flavor of it is a snark, another one is a stark, and yet another one is bulletproofs. And, maybe as a recap, what is a zero-knowledge proof? Like in a zero-knowledge proof, I can prove you that something is true without telling you why it's true. So I can prove to you, for example, that I know where Waldo is without giving you any information about where Waldo is. And you will be convinced that this picture has Waldo on it, like there's a Waldo here. But you're also convinced that I know where Waldo is, but you have no idea where it is unless you figure it out yourself. And one way that this is used in Bitcoin is that I can have a transaction which doesn't have, or in cryptocurrencies that I have like a cryptographic transaction where a lot of the details are hidden, but I can still prove to you that the transaction is valid without giving you any information about why it's valid. And bulletproofs is one particular zero-knowledge proof that has sort of different trade-offs to other zero-knowledge proofs. So the proofs are very short. They're not quite as efficient as snarks, but snarks have this downside that when you use snarks, there's this sort of trusted setup which creates toxic waste. And the problem is if this is not done correctly, or if someone, you need to trust someone to create a so-called proving key and a verification key. And if they cheat, then they can create proofs about statements that aren't true. So they can, for example, prove to you that they know where Waldo is without actually knowing where Waldo is, or without there even being a Waldo. They can prove to you that a transaction is valid, but actually they just created money out of thin air. So that is obviously not a very good thing. And, you can sort of try to circumvent that, but it's really, really difficult sort of with snarks. And bulletproofs do not have this trusted setup. So that is sort of the big benefit of them.
I want to dig into the trusted setup in more detail soon, but you just mentioned something that ZK snarks, they generate a toxic waste. What do you mean by that? What is that?
This is the trusted setup. Sort of, this is sort of the terminology that Zcash uses is that the setup, this ceremony, like generates, toxic waste in the sense that if that toxic waste isn't discarded, if the person who does the trusted setup doesn't, delete that, then
vulnerable.
Yeah, then wow. This toxic waste can be used to create the false proof.
The toxic waste like software and hardware and
it's a secret key, secret special key, like a 32-byte key, and if you have that, then you can prove whatever you want. And the way that it's usually done to sort of prevent, like you could trust, you could get, I don't know, the Dalai Lama to do this, and everybody trusts that he's a computer expert and will do this properly. But the other way to do this is to say, like, we'll get a bunch of people together and they have to do the trusted setup together in such a way that as long as one of them is honest, so as long as they don't all cheat or like collude together, then the toxic waste is sort of properly discarded. But this is extremely complicated and takes a lot of time and has it's basically costly, but doable. So Zcash did this, and Zcash works. But there's downsides to it, and bulletproofs do not have this downside.
They don't have trusted setups. They don't produce this toxic waste. They are faster.
No, so that's a very,
maybe something we can touch on later on.
Right. Like faster is like sort of like a 10-dimensional question,
okay,
right?
Gotcha.
And in some ways they're clearly slower, and in other ways they're faster.
Well, we have the whole episode to kind of go into the nuances of this, but maybe we start with a little bit of a history of where the bulletproof idea came from.
So the Bitcoin core developers, Peter Woolley, Andrew Poelstra, and Greg Maxwell, they sort of approached us with this problem. They had invented this thing called, or Greg Maxwell had invented this thing called a confidential transaction. So what is a confidential transaction? It is a confidential transaction looks like a Bitcoin transaction, with the one difference that the amounts that are being transferred are encrypted. So no one is able to see how much is being transferred. The problem now is obviously how do miners check that the transaction is valid? And, now if you've listened to maybe a couple of the previous episodes, right, you should know the solution for this is a zero-knowledge proof, right? I prove to you that the transaction is valid. I prove to you that, the sum of the inputs to the transaction is equal to the sum of the outputs. So there's no new money created. And I do this without giving you any additional information. The problem is that the zero-knowledge proofs that they used, it's like a special case, and it's called a range proof. They were very, they were pretty large, It would mean like that every transaction is like 8 kilobytes, which really isn't, limits scalability, which is another big issue in cryptocurrency. So, it really would have made transactions a lot more costly, and the fees would be higher, and sort of the question that they came to us with is there a zero-knowledge proof, and especially one without a trusted setup, where the proofs are shorter? Can you come up with a problem? So they approached my advisor Dan Bonet and me, and sort of gave us this problem, and I was a new PhD student, sort of looking for interesting problems in that space, and then we started working on this, and we found this amazing prior work by people from the University College London, Jens Groth's group, and which had sort of, gotten us a lot of the way there. And then, we sort of improved on that work and used sort of techniques from that work to develop bulletproofs, which happened to work extremely well for confidential transactions. But it then turned out that, this is also doesn't just work for confidential transactions, but you could sort of use it for anything, like anything where you can use a snark, you can use a bulletproof instead. And that doesn't mean that you should use a bulletproof instead, because, snarks are, in some ways, they're way more efficient, but at least you can. And so that's how sort of this started.
What year was that? This is 2 years ago?
No, this was like a year ago. So, well, like, you work on it for a year, and then a year ago we published it. So I think we put out the paper in like November 2017, which is, it's quite cool and amazing about the space, how quickly things, get deployed in practice. And this is not usually the case for academic work, that things get, rolled out that quickly, get that much attention that quickly. And I think, this speaks to sort of the cryptocurrency space really being interested and open into new academic ideas, which I think is amazing.
Yeah, and an eagerness to sort of explore new stuff and try to innovate.
Yeah, right. Yeah, and
privacy is a big issue, always hasn't been a big issue for blockchain. So I think everyone is sort of keen on trying to use whatever they can to just make it better.
Yeah.
We spoke yesterday briefly about the naming and how that was very well thought. I don't know, Bulletproofs has this awesome sound to it. And it's like, I don't know, there's something, I know this is going to sound sort of funny, but it's like, I wonder, like, how did you come up with that name, basically?
Yeah, so
and has that helped?
Yeah, no, I'm sure it helped. Branding is important, I think it actually is really important. So a friend of mine, I was like, we had written the paper, I had the idea, and then, I was talking to a friend of mine, Shashank Agrawal, who is also a crypto researcher that I work with. And he, I was like saying like, hey, we have this new zero knowledge proof. Like, do you have any ideas? Like, spitballing ideas and for names. And he said, yeah, why don't you name it Bulletproofs? Because it's a short proof, and then sort of it's fast, I guess. And but it's also it's secure, right? Like, yeah,
it's really good.
It doesn't have the toxic waste, the sort of the hole there. And, so that was sort of the name, which, in some ways it's a little bit gimmicky, but, in other ways it's sort of, it eases up the conversation about it, right? Otherwise often papers get referred to by, you take the initials of the authors and add the year, which makes it, like GKR 87 or whatever. And like, if you're really into the community, you might know what that is. I think GKR was later, but the sort of for the general public, sort of, nice names like Snarks or Starks or Bulletproofs, right? Like, that definitely helps.
So digging in a little bit more into how Bulletproofs actually work and like what the details are, I'm just curious. I mean, if we set it in this landscape, we've talked a little bit about in the intro episode how there's interactive zero knowledge proofs and then non-interactive zero knowledge proofs. ZK Snarks are non-interactive, so are like most other popular ones. Bulletproofs is non-interactive.
Yeah, it's actually interesting. That's not 1000% true technically, because it's an interactive proof that you can turn into a non-interactive one. And that's actually true for a lot of the protocols. There's sort of a generic way of turning these interactive protocols into non-interactive protocols. But it seems like really, that non-interactive proofs, especially in the blockchain settings, have a lot more advantages, because the idea is, right, an interactive proof requires a specific person, like it's, me trying to convince someone else, and they get to sort of ask questions, and, then I answer them. But in the blockchain setting, right, like, everybody wants to check the proof, right? It's not just one person that wants to check it. So you really need something that you can just write down, like a proof that you can write down, and then everybody can read the proof and check it. And that's sort of what a non-interactive proof is.
So zero knowledge proof, or like proving functions, are built on these circuits. It's usually something like implementers of this talk about, like this circuitry, and when these circuits are slow or they're hard to construct or whatever. What is it in a bulletproof that separates it from like a snark? Is it some aspect of this circuit structure, or is it something else?
Yeah, so the circuit is usually the way that you express what you're trying to prove. So say I want to prove that, this transaction is valid. this is sort of a very generic statement, so you need to make it more specific. And basically the way, like the circuit is almost like the programming language, or it's more like the assembly. So, you write down that statement in terms of like multiplications and additions, right? You really break it down to the core. And then you can take that circuit and then create a proof, sort of, what you do is you write down the circuit, and the zero knowledge proof is, I know secrets inputs to the circuit that at the end of the circuit, if you speak in electronics, like the light turns on, or in math, right, the output is 1 of the circuit, right? It's a bunch of multiplication gates and addition gates, and then at the end, what comes out is 1. And what I prove to you is that I know values to the circuit such that the output is 1. I'm not going to tell you what these values are, but I know them. And sort of this circuit architecture, this works for, you can take the circuit and then produce a snark that the inputs for the circuit, or you can produce a bulletproof. So what is different, the differences are in the properties, like how long is the proof? How long does it take to check it? How complicated is it? Or like how long does it take to create it? That is really where the differences are. And for example, like snarks are usually shorter and easier to check than bulletproofs. But bulletproofs are still sort of, still very short. That's the main sort of property that we're aiming for, especially compared to more like, the solutions that were used before that didn't have a trusted setup. They're way, way shorter. So this is sort of the key property that we were aiming for. And why do we care about short proofs? Well, they're sort of in a blockchain, everybody, it's decentralized. So everybody is supposed to have the blockchain and read it. And if suddenly the blockchain gets bigger and bigger, then, everybody needs to download it and send it to each other. And that really creates bottlenecks. And that's why we care about making everything that is on the blockchain. So for example, the transactions and the proofs as short as possible.
So short here means like few bytes.
Few bytes, yeah. It literally means, bulletproofs are basically like less than, they're 1 to 2 kilobytes is like the order of magnitude. And snarks are like 200 bytes, talking.
But so conceptually, it's sort of like you avoid this trusted setup by including more information in the proof. Could you say that?
No, it's not impossible that we could have a proof that is as short as a snark without a trusted setup. But, it just sort of, we just don't know yet how to do it. Of course, like, basically a trusted setup gives the designer of the proof more freedom, right? This is a thing that you can do now, and the trusted setup can do some things. And like once you remove that freedom, you make the task harder. So it sort of seems natural that you have to do some trade-offs there. But, like there's no reason to say, we can't get even better, right? So we'll see sort of what happens.
So going back to like placing this in the universe of zero knowledge proofs, how does this compare to, we've talked a little bit already about snarks, but there's starks and there's these other things. Like where does it live and how does it compare to these things?
I would say, right, like compared to snarks, I would say you should sort of use a bulletproof when you want to use a snark, but you don't want to do the trusted setup. And it's okay if the proofs are a little bit like bigger and take longer to check. And so, for example, compared to starks, the proofs are a lot shorter than starks. So starks is another proof system that doesn't have a trusted setup. And there the comparison is a little bit more difficult because starks are even larger. They're significantly larger, on the order of like 100 or 200 kilobytes. And this becomes, something that where you wouldn't want to do one stark per transaction. That, like if every transaction is 200 kilobytes, then, this really becomes a problem. But starks and snarks have this amazing property that you can prove, I can prove to you that some really, really complicated statements. So for example, I can prove to you that I've checked the whole blockchain, or I've checked all of the transactions on the blockchain, and all of them were valid. And now to check the proof, this is faster than if you've even had all the transactions and checked them individually. So, right, I can go through all of the transactions, one by one, and, check that they're correct. Check the signature, check that, the inputs and outputs are correct. And the amazing property that both Snarks and Starks have, and bulletproofs do not have, is that you can create a proof that is shorter than all of these transactions. That's also true for bulletproofs. But what's even more important is that checking the proof might take a millisecond versus checking all of the transactions takes an hour. So now you have this compression property where I don't even need to, right? I can give you sort of the blockchain, or I can give you just the head of the blockchain, and then a proof that everything before that you don't even need to look at was done correctly. And this sort of allows for amazing, cool new applications where you have sort of clients that don't even see the whole blockchain, but they know that, this one hash of the blockchain is the correct hash. So I can, now you have the basically the whole blockchain, and you checked it, and it's like a 32-byte hash. And this is really where, for example, Starks shine, and Snarks can also do that. But again, you have the trusted setup.
Something we've touched on a little bit on this podcast before is stateless clients. Mm-hmm. And when you start talking about stateless clients, usually some sort of zero-knowledge proof comes in the discussion because of exactly this property, that it's sort of a compression.
Exactly. So that is exactly
factor.
what I was talking about. And the amazing thing is here, you don't need to. So here comes another sort of technicality, is that for these stateless clients, you don't even care about the zero knowledge. You care about the proof part, right? So I don't want to hide from you the rest of the blockchain. It's not that I don't want to give it to you. It just is more efficient to give you a proof that it was correctly, right? So you don't need sort of all of these proofs have sort of a zero knowledge variant and a non-zero knowledge variant. And for a lot of these applications, you don't even care about the zero knowledge part of it. You just care about the compression part of it. And so bulletproofs are not, you can shrink the size, but checking the proof will still be sort of, if I give you a proof that, I checked the whole blockchain, then I can give you sort of checking that will be as long as checking the whole blockchain, or maybe even, maybe even longer. So for stateless clients, bulletproofs are not a good application. They are not a good tool. But for something like a transaction, I want to prove to you that a transaction where I actually want to do the zero knowledge part, right? Where I want to hide the details. That is where bulletproofs are really valuable.
Going back to Snarks and Starks, the image I have of Starks, I'm not actually sure where I've gotten this from, but that Starks is more intended for general computation, like prove that this program was executed correctly. I mean, that's what all of them do, but that Starks allow for larger programs.
So, yeah, it's really hard to, sort of, there, the differences are nuanced, and I wouldn't necessarily say that. The weird thing is that Starks aren't necessarily they aren't the only thing that work for larger programs, right? Or doing that sort of a larger general purpose computation works. The thing though is that Starks are fairly large, right? So they only really make sense for larger programs. It's not that they only work for that, but this is where they sort of shine and where they make sense. So you can do that with you can do that with a Snark, and but I feel like this is sort of the reason why Starks are sort of presented in that way, is because this is where they shine the most, right?
That makes sense.
So this is sort of their distinction.
You've mentioned Snarks, Starks, bulletproofs. Is there anything else?
Yeah, there's a very good question. There's a lot of other things. So, for example, there's Hyrax, there's Ligero. For example, Hyrex, like the thing is they're sort of in the more in the middle of the trade-off space. So, Hyrex has like a good trade-off between, the size of the proof and the verification time. And Ligero, for example, is really interesting because it's creating the proof is very short, right? For all the other ones, sort of creating the proof is somewhat tedious. There again, Bulletproofs has, for example, compared to Snarks, Bulletproofs has the advantage. It takes maybe roughly the same time, but it requires a lot less memory. So you can sort of do it on a smaller machine, which may be nice. Ligero, for example, is fast to compute, and this is a really hot space. So, when new stuff is coming out, and I know lots of people are working on it in the academic community, and, partially driven by cryptocurrencies, right? Like zero knowledge proofs have been around for like since the 80s, I think. This is really being driven by sort of these new applications, because previously, it was a cute sort of theoretic concept, and now, this can actually be used in public and secure sort of billions of dollars, which
it's motivating.
It's motivating, right? There's.
I have heard of. I was talking to Howard Wu, and he mentioned they'd worked with a big bank that was like they had a zero knowledge proof structure to basically interact with on behalf of customers with other entities. So if like an insurance firm will only give you an insurance if you have more than $1 million in your bank account, then the bank can generate a zero knowledge proof that they have that without saying how much money they have.
Yeah, no, there are definitely a lot of other applications to zero knowledge proofs. For example, one is voting is like a common one that is referred to, right? I want to prove to you that my vote was done correctly and that. But I don't want to tell you what I voted for, right? So that's a very like sort of an application. But for as you were talking about banks, so we have this paper on how Bitcoin banks, so Bitcoin exchanges basically, can prove that they're solvent without giving up any information about how much does each customer have? How much Bitcoin do they have in total? Which addresses do they control? All of that remains private, but they can still prove that they have more money in their Bitcoin addresses than they owe to their customers. And the cool thing is that what I really liked about this paper is that this is something that you might want for your normal, like your fiat bank, right? But there's sort of no way, like even conceptually, there's no way that they could do that because there's not like this public ledger, right? The blockchain, which you can sort of prove the statement against. And, here sort of the idea that Bitcoin and all these other currencies are cryptocurrencies, that they have this cryptographic ledger, really makes this possible.
I have a little side question before we move on. Something that I know is like a problem in this space and that I was fascinated about when I first found out was that we spoke a little bit about these circuits, and you said like, yeah, you could design your circuit and sort of use any proving, app structure to run it, kind of. But there's no standardized format of how to write such a circuit. So you can't actually like define it once and use different proving algorithms on it.
Yeah. So, I mean, and the statement that I said was true in theory. In practice, it's probably not,
Have you seen any work towards like trying to standardize that
Absolutely.
Assembly language?
So there was just a couple months ago, there was a workshop in Boston and Cambridge, where a lot of the people that work on zero knowledge proofs, a lot of the academics and people from industry came together, and the goal was to standardize zero knowledge proofs. It was exactly that, sort of work on that, and all of the big names, Shafi Goldwasser, who got the Turing Award, the Nobel Prize for Computer Science, partially for inventing zero knowledge proofs, was there. And we started sort of working, and we've put out some documents on like working towards standardization. I'm a little bit, while I think, this is, in some ways I think it's a good idea. In other ways, I think I'm, you should be cautious, because sort of you don't want to stifle innovation, right? And you don't want to say, this is the one thing that we use, and no one, should use anything else.
Maybe it's a bit premature.
I think it's a little bit premature, right? Because there's still, there's papers still coming out, this is still being developed, and we don't know what will come out in the future. So I think you have to be sort of strike a good balance. And I think, a lot of work has to go and is going into sort of tooling. So, application development, making it easy to use these tools, right? Like, abstracting away this language. I hope that, in the future, right, you shouldn't spend as much time writing these circuits, or these things should become, right, like maybe you can write your zero knowledge proof system in Rust or whatever, and then it gets compiled down. There's some work on this, taking C, but, it's just not efficient and doesn't work as well as you would hope. But this is sort of, I think this is still coming, like a little bit more patience. But I think this is sort of really, really important work, making it easier to use.
So we've been talking sort of about general bulletproofs and where it lives in comparison to other zero knowledge. Actually, what do you call these? Zero knowledge applications? Zero knowledge
proofs.
You just call bulletproofs a zero knowledge proof.
Yeah, it's a zero knowledge proof. So and then there's also, like, technically it's a zero knowledge argument. There's like proofs and arguments, and everything sort of that you see, like, so SNARK means succinct, non-interactive argument of knowledge, and bulletproofs is technically also an argument, but that's sort of it's really only a technical detail, and it doesn't matter. All of these things are zero knowledge proofs.
Okay, so
more technically, there's zero knowledge proof systems, and then you can use them to create a zero knowledge proof.
So far we've been talking about zero knowledge proof systems, but at what point does this apply to blockchain? And because as we've heard, there's all these examples that are not blockchain. How is that interacting? How are you seeing these systems starting to interact more with blockchain?
Yeah, so sort of you have these zero knowledge proof systems, and then you have applications that sort of require zero knowledge proof. And a lot of these applications are for blockchains, right? So you can prove that, as I was saying, you can prove that a transaction is valid without giving up any information about why it is valid, right? And everybody is convinced, and is sort of, all the miners need to check transactions, right? They need to check that a transaction is valid. They need to check the signature. And in some ways, a signature, so cryptographic signature, is a special kind of zero knowledge proof, where you prove that, you basically prove that I know the private key to this Bitcoin or this cryptocurrency address, but I'm not going to tell you what the key is, because otherwise, you could sort of create signatures yourself. I don't want to give that up. But here, sort of, this proves to you that I know this, and also, and through that I can authorize a transaction.
And was that sort of the first thinking about applying zero knowledge proofs into blockchain?
That's sort of just saying that even blockchains that don't use zero knowledge proofs, they basically use something very that comes from zero knowledge proofs, akin to it, right? The signatures that I use are basically zero knowledge proofs. And the other thing is, once in Bitcoin, a transaction is, so most cryptocurrencies, transactions, you can see, everybody says, like in the beginning, everybody says, Bitcoin is private or whatever, it has a lot of privacy. But that's actually not really true, because you can see which address spends to which address and how much is being sent. And there's been a lot of work on showing that you might not know who this address belongs to, but there's been a lot of work showing on de-anonymizing them, like, showing this address belongs to Silk Road, or this drug market, or this address belongs to this company, belongs to Coinbase or whatever. And and there's been a lot of academic and work, and also now there's companies, and the FBI actually kind of likes Bitcoin for that reason, because it's able to trace the payments really well. And then, say you receive in some maybe distant, maybe not so distant future, you receive your payment, your salary in your favorite cryptocurrency. And then that payment is public on the blockchain, right? Your salary is public on the blockchain. So everybody can see how much you're making. Or say your company and you want to buy, I don't know, you want to buy your supplies, right?
You've negotiated something.
Say you're McDonald's and you want to buy ketchup from Heinz, right?
Yeah.
Like they probably get a way cheaper price than their competitors, and Burger King would like to know how much they're paying, right? This is an important business secret, right? That neither McDonald's nor Heinz would like to give up. But if it's done on the blockchain, everybody can basically tell how much it is. So this makes it really almost unusable, sort of, for people to use the blockchain. And then there's the whole sort of, if you're, say, you're a political dissident, right? Or you say you're somehow, you don't want the government to know your payments. Like even if then they can see who you're paying to, right? And you say you're sending money to Snowden, right? In Russia, then, if the US government can see that may be a problem, because they don't like that. And, for all of these reasons, we would like to hide all of this information, right? We would like to hide who's paying whom, and also, sometimes you don't care about hiding who's paying whom, and then you would still like to hide how much you're paying. And I think sort of the best example for that is there's in the US, there's the popular payment service Venmo, where you can pay people, which is really popular. And even there you can choose whether you want to make your payment, who you're paying, whether you want to make that public. But sort of the default is like, or you can't even change, sort of, you can never sort of show how much you're paying, because no one would want that, right? Like you wouldn't want to, let the public know how much you're paying your buddy for rent, right? This is just sort of this seems very naturally like we don't want this information out in the public. But in Bitcoin and in most of the cryptocurrencies, it is. So zero knowledge proofs are sort of the workhorse here that can help us prevent this, because you now want to prove, right? It's this dichotomy that you want to have the transaction be private, so you use, say, encryption to hide some of this information, but you still want everybody to be able to check which transactions are valid and what is not. So here, this is where zero knowledge proof systems come in. I can prove to you that the transaction is valid without telling you why.
So bulletproofs, like you mentioned, it's sort of driven a little bit by the Bitcoin core developers, and can be used to implement confidential transactions on Bitcoin.
Yeah. And I think they were actually sort of the main thing that what they were thinking about is Mimblewimble, which is a new blockchain design, like a very sort of simple, in some ways simple but beautiful blockchain design, like a sort of minimal, which also uses confidential transactions at the core of it. And lots of people have been working on that, and there's been a lot of interest in that. And there they were. Mimblewimble allows you to sort of shrink the size of the blockchain a lot, but then they were like, yeah, we can shrink all of that, but what we're left with is sort of these confidential transactions. And currently, before bulletproofs, they were 8 or 10 kilobytes or whatever per transactions, and now with bulletproofs you can get that down to like less than a kilobyte, and it depends on the parameters, right? Like it can shrink by like a factor of 10 or even more. And that made it a lot more feasible.
Yeah, so that's what I was gonna ask is like, where do you see implementations of bulletproofs, and like what do you see now and what do you expect to see in the future? Like which specific projects do you think will implement anything?
So right now, so Monero has implemented bulletproofs, and they will sort of, because they already use confidential transactions, and for them, it was just a clear win. It's sort of faster, it's smaller than what they previously used. It will lower the fees that Monero users will have to pay. So they've they're doing security audits right now. They've done security audits and to make sure that the implementation is correct, right? There's always two things, there's sort of the theory behind it being correct, but then you can implement it and you can screw that up like massively. And that's where actually a lot of the problems in computer security come from is sort of bad implementations or faulty implementations. So they've done, a lot of work on making sure that is correct. And then they will deploy it. I think they will try to deploy it this year. So sort of, within a year of publishing the paper, Bulletproofs will secure, I don't know how much Monero is worth, like $1 billion.
I don't know either.
What about something like Zcash? It already it's built very much around ZK snarks.
Mm-hmm.
Is there a way for ZK, would it make sense for Zcash to also be using Bulletproof?
Yeah, so that's a very good question. So we've, I guess, we saw each other at ZKon0 and they presented Bulletproofs because they're certainly interested in it, right? And for Zcash, it's not as clear cut as for Monero. For Monero, it's clearly better to use Bulletproofs. For Zcash, there's a trade-off. So basically, using Bulletproofs would make verifying the transaction and checking the transactions, so it would make the work for the miners more difficult, but it would remove the trusted setup. So there is sort of the trade-off, and they are I think it just requires more exploration. I don't know what the answer is. I think it depends on many, many different things. But I think it's definitely worth exploring. And I've been in contact with them, sort of, exploring that idea.
What about, you mentioned Mimblewimble. Are they also going to be using Bulletproofs, or do they already have sort of enough confidentiality built into the protocol?
No, so Mimblewimble already uses a zero knowledge proof, a so-called, basically it's called a Sigma protocol, or closely related to something called a Sigma protocol. Or the original design is, Mimblewimble doesn't exist yet. Sort of there's, Mimblewimble was just for a sort of historical reference, it's actually a great story. It was this random guy that just dropped the link on one of these IRC channels, a Tor network link, sort of a hidden link. And this guy was named, what was it called? It was the French name for Jedusor something. It was the French name for Tom Riddle from Harry Potter, which...
We know how old this person is for sure.
Yeah, exactly. Yeah, the name has to be Elvis Jedusor because, right, Tom Riddle is a, you can make I am Voldemort out of sort of these things. I don't know, and Je suis, sort of in the French version, the name had to be different. Either way, so this is where all of this came up. And this guy just, anonymous, we don't know who he is. Just like Satoshi, he just dropped sort of this new design of a blockchain called Mimblewimble, which is also a spell from Harry Potter. It's all very Harry Potter themed.
Yeah.
So, he just dropped this design, which turned out to actually be a quite neat idea. And then, other people like Andrew Poelstra, for example, have sort of kept driving that idea forward and formalizing it. And so they use a zero knowledge proof. And the sort of the best one for them available is also Bulletproof. So they will they will use. I'm pretty sure that any sort of reasonable implementation of the protocol should use Bulletproofs.
Would they do something like take Bulletproofs and run with it? Will they change it?
No, I think they should basically just take it and run with it. You sort of I don't know what they will do for their implementation, whether they will implement it in code themselves or whether they will take one of the existing implementations. I honestly don't know how that's going to work. But in general, when you design sort of these systems, you shouldn't, it's better to not design it with one specific. You should just design it to say here I need a zero knowledge proof. And then later, you can pick the one that is best, right? It should be sort of, you shouldn't say, Zcash, like zero cash, is based on an academic work. And there they also say, like, we use a zero knowledge proof to create this. So they already had sort of this abstraction in mind. And then they say sort of the best one that we can use to make this practical is ZK snarks, right? But, they already sort of acknowledged that you could use any zero knowledge proof to do this.
And so this sort of speaks to something currently, like we've talked about a few different protocols, blockchains, and how they're using these different zero knowledge proofs, so these different zero knowledge proof systems, but they're not necessarily tied to each other. Like they're interchangeable.
Yeah, exactly, right? Like, one is sort of this is like, saying, I think the Bitcoin is mostly written in C, and I think, the main Ethereum client is like one of them is written in Go, and, whatever. But like, Bitcoin and C have like, that's not, those are just completely orthogonal things, and Ethereum Go or whatever, or like, I don't know, Rust or, those are just, one is a tool and the other one is sort of the application. And,
they're interchangeable.
I think, yeah, they're at least to some degree, right? Like, it might make the most sense to use one with another. That's clearly the case, but there's sort of still, I think having this abstraction and keeping those things separate, I think is really important, and not get those things sort of conflated with each other. And, you were also saying sort of, I want to say one other thing you were saying earlier, how, which projects are currently using it and which projects might be using it. I really hope that, in the future, sort of everyone, like right now there's privacy coins, right? There's like Monero and Zcash that sort of the focus is on privacy. I really hope that sort of, that privacy will become the default. That sort of everyone will have at least sort of some level of privacy, at least like confidential transactions. Like that should be the norm rather than the exception, right? Because the problem right now, if you're using Monero or Zcash, to some degree, like you might get asked, like, why are you using this? Are you using this to buy drugs, right? You sort of like, you make yourself almost more suspicious by just using these coins, even if you're just using them for your everyday payments, which is sort of a bad state. But if sort of this becomes if privacy is the default, which I think in general should be the norm, then, everybody benefits from it. It becomes a public good, where sort of everybody has the benefits of not being, suspicious and just saying like, hey, this is sort of what happened when WhatsApp became, and Signal and sort of all of these messages became end-to-end encrypted. Now you don't have to, previously there were also end-to-end encrypted messengers, but suddenly as soon as you use that, you probably got put on some CIA list. I don't know, making things up here, but now if it becomes the default and everybody uses it and everybody expects it, and that's a great thing, So I hope we see that for sort of transactions also becoming private in the future. But, I think this will still take a couple years.
So at the beginning of this episode, I said, like, we're talking about bulletproofs and maybe some other things. You obviously work on a lot of other things than bulletproofs, even though that's been the main topic here. Could you give us just like the quick pitch on what other stuff you have going?
Yeah, so one thing that I've focused on, or we've focused on sort of recently, has been these things called verifiable delay functions. And this is something, very technical, which has a lot of surprising applications. So what is a verifiable delay function? So in a nutshell, it's just a function that takes a long time to compute, no matter whether you're Amazon and have a bunch of like data centers, or whether you have an ASIC, or whether you're just on a single computer. The idea is that you cannot speed it up. And why can you not speed it up? Because you cannot use parallelism. It's a sort of sequential function. So you compute one step after another. And the way that, ASIC speed things up is by parallelizing things massively. So verifiable delay function is a function that takes a long time to compute. But it's easy, once you've done it, it's easy to check that you've computed it correctly. So, sort of maybe inverting it is really, really fast. So why in the world would I care about this? Well, it lets you sort of, it has a lot of applications where, for example, I can prove to you that this blockchain has existed for a long, long time, right? And the way that I do that is I just take sort of, or this block has existed for, 10 minutes. And the way that I do this is I take the blockchain and then I compute a verify with delay function. And if I give you a verify with delay function that, you sort of know how long it will take me to compute, like it's sort of almost like a clock, it's not an exact clock, but it almost is like that. And if I if I give you a verifiable delay function off it and it took me 10 minutes to compute, then you know that this block must have existed 10 minutes ago. So I can use this to, for example, prevent in these proof of stake protocols, like there's one attack where, create a sort of blockchain out of thin air from the beginning. Because now suddenly it doesn't take proof of work anymore. It's not expensive to create a proof of stake chain.
AKA a long range attack.
Exactly. A long range attack is sort of the name. And with the VDF, that's one way to, for example, prevent that, because that, I need to, if I have this VDF running on this blockchain, I know that, okay, this blockchain must have existed a year ago, right? This must have existed 2 years ago. But checking, computing the function takes 2 years, but checking it is like milliseconds. And another really, really cool application that was maybe our initial motivation is that it comes from lotteries. And so there's this idea that you can use sort of Bitcoin, and it doesn't actually even have to be Bitcoin. It's like, say I want to run a lottery, okay? And you should all Google this video on, I think it's a Romanian lottery, where usually the way that we run lotteries is like we have these public drawings, right? Someone draws some balls and out of like whatever this tube or this spinning thing, and you can see sort of this they're drawing the balls, and you can see that 3 balls have been drawn. But sort of on the digital display, it shows like 5 balls, right? And the reporter is like really confused because she also sees that, and even though it's a live ball drawing. And then the next 2 balls come sort of out of the thing, and surprise, surprise, they're exactly the same balls that have been shown, that they were shown on the digital thing before. So, maybe they sort of rigged the system and someone got really lucky and won the lottery, like really lucky. And they just sort of messed up the graphics on the thing. And how can we, trust these drawings? How can, or if you shuffle cards, right, there's sleight of hands and there's magicians that can do things. So the question is like, how can we run a lottery where everybody can trust the randomness, without having, again, a trusted party, this again where a trusted party makes the thing easy, If you have a trusted party that tells you a random number or that rolls, a dice and does it correctly, then everything's good. But maybe we don't want to trust anyone. And these lotteries, they come up all the time. For example, in smart contracts, you might have sort of random, like every time, randomness comes into play. And the idea was that, you can, for example, take a block header and extract some randomness from it. Or you can also take, another one is you can guess on tomorrow's NBA games, right? And say whatever, I'll the scores of the NBA games, they will sort of determine the digits of the random number. The problem is that, in an NBA game, I can bribe the players, I can bribe the refs. In sort of a blockchain, I can bribe the miners to, whenever the block header doesn't give me good randomness, they will throw it away. They will sort of decide to, when, say we do $1 billion coin flip, determined on the block header. I'll just take up a loan of $1 million and bribe the miners until I get heads and win the $1 billion. So that sort of doesn't really work. And the idea is that you can now use the verifiable delay function by sort of saying, okay, we'll take the scores from the NBA games, or we'll take the block headers. And then on top of that, we'll, compute an hour-long delay or a day-long delay. And then only then, this will be sort of the random number. And what that means is that
it's impossible.
It's impossible because, I don't know which numbers will be good for me because I wasn't able to compute this VDF, verifiable delay function on top of it. So how will I, how do I know who to bribe or what to do? And, I can, the NBA games will be over by the time the verifiable delay functions, by the time how I know how to influence the scores, the sort of the game will be over. And, or the games will be over. So that's sort of where a verifiable delay function can be used to run a lottery, and this has many applications again in proof of stake where again, right, like in a proof of stake, so things are a little bit more complicated, but there I basically need to pick random, some random people randomly who are the next sort of block validators, right? Everybody has some stake, and then one of them or some of them are the next leaders. And how do I pick them? For that, I need good randomness. And here sort of a VDF can help.
Yeah, so in proof of stake systems, like you say, there's a problem the problem is not the consensus algorithm. Like you can have PBFT that's been around for a really long time. The problem is if you have a validator set of 10,000, you can't run PBFT among 10,000 people, so you need to choose some subsets. And that's the hard problem. But you also have a bunch of other hard problems, which is essentially like Sybil resistance, which we were talking about before. So yeah, that's an aspect of it that I'm really interested in, is using delay functions as a Sybil resistance mechanism.
Maybe just to wrap up, let's go back to bulletproofs for a second. What's the future of bulletproofs? What are you working on next?
I hope sort of one future will be a lot more people using it. Sort of also maybe, people developing new libraries to make the usage of it easier. And then, there's still interesting academic questions. How can we make sort of the time to check the proof? Can we sort of bring that down? Can we make the proofs even smaller? So can we, combine proof systems in some crazy way to sort of get new properties? And so both on like this sort of side, can we improve the proof system? And can we find also new applications? Can we say, here's this problem, and now we can solve this really nicely using zero knowledge proofs or using bullet proofs. So that's sort of, the questions that I'm interested in, and I really, really hope that other people are going to work on.
You also mentioned that there's a conference coming up that you were a little bit excited about. Do you want to share that?
Yeah, I definitely want to pitch that. So we have the Stanford Blockchain Conference, or formerly known as BPACE, which is, so the third edition is going to come up in, I think it's January 30th. And right now you can submit academic papers. So it's an academic conference on blockchain research.
What's it called?
The Stanford Blockchain Conference. Just Google that and you will find it. Or I think it's cyber.stanford.edu/SBC19. So, right now there's sort of the submission process of academic papers, and we'll select the best papers and presentations that will then get presented at the conference, and you can also attend it. I don't know what, I'm sure it's going to be cheap. So it's not about, it's going to be very academic and really trying to sort of push on the edge of research, and sort of the cutting edge research is hopefully going to be presented there. And this is all part of the, so Stanford announced that, or the computer science department, announced the Center for Blockchain Research. What this basically is sort of a concerted effort into blockchain research by professors from the computer science department, and also some lawyers from the law school. And so I think that they have sort of noticed blockchains, which I'm excited about, and sort of are notice that it's interesting from an academic point of view. And are trying to, sort of push the cutting edge.
Well, I think on that note, thank you so much for sitting down with us and exploring this sort of advanced zero knowledge proof system, bulletproofs, and helping us get inside it. I think it's been really informative.
Yeah, thanks for having me.
Thank you very much.
And to our listeners, thanks for listening.
Thanks for listening.